Hey guys, Mr. Myers is here for a live stream on calculus. We're going to be doing some, now it says live. Hey guys, we're going to be doing some calculus tonight. My students are studying for an exam, and we've got some problems that they've asked for me to look over and talk about some concepts. So for the next maybe half an hour to 45 minutes, I'm going to be going over some problems. The problems are from the Essentials of Calculus text. And we'll be talking about a lot of different things here, everything from derivatives to antidifferentiation. It looks like there's some questions on max and mins, and gosh, just all kinds of things. So let's go and get started. And if you have any questions that I did not get to talk about, you can either put them in the comments below, or you can, if you're on the live stream right now, you can go and take a look at the group chat. And if you are one of my students too, you can also send me something on Remind, and I can see if I can go through it. But I've got kind of a lot of problems to go through, so I'm going to try to go through this as best as possible. If you do have a question, like I'm going over something and you're like, what's he talking about? Or can you go over that one more time? Just go ahead and send me, if you're one of my students, send me a text on Remind, and I'll see if I can answer that. All right, so let's get to it here. Folks, let's see if I got my, let's see here. So there we go. Okay. So let's go to, here we go. Hopefully you can all see that. This is our review section here. And if you guys are in my class, yes, we are having class tomorrow. We're here in California. For those of you that are not, we're here in California, and it's been very smoky with the fires lately. And so we've had some other schools canceled in the area, but our school, actually in the area, the high schools are all still open, but some of the universities are closed. But it's a very tough time for a lot of Californians. So our thoughts and prayers go out to those. But let's get into some calculus, because we are going to have a test. So let's see. I'm going to start with, that's not what I wanted to do. Hold on a second. I just got to move something around here. Okay, so let's see here. I would like to start with number 6. That came up a couple times here. So let's go and start with number 6. Let's see here. I want to make sure that everything's showing up correctly. Come on. All right. Sure. Okay, so it should be working now. Let's go over number 6 here. If there's any problems, like you see, like something isn't showing up like it's supposed to. Right now I'm supposed to be working on number 6. If it's not showing up, just for those of you, just put it in the chat, or go and let me know. Okay, so we're looking at local linearization. And local linearization is the concept or the method of estimating things by using a tangent line. So whenever you see local linearization, or we're trying to estimate something, we're estimating using a tangent line. So all we're going to do is find the equation of the tangent line. So we've got to find the derivative, because we need the slope of the tangent line. And we're going to use the points for the x1 and y1. We're going to find the equation of the derivative, and then we're going to plug in whatever we're trying to find the estimate of. Okay, so an interstate, use this data to write it. Okay, so first of all, this should be these data. That's the stat teacher in me. An interstate driver is traveling 420 miles across the state from south to north without stopping. At noon, she noticed her speed is 60 miles per hour, and her position is at interstate mile marker 240. Interstate mile marker increases from south to north. Use these data to write a linear function, which could be used to estimate her position as a function of time. So we need to find the slope of the tangent line. Y minus y1 equals m times x minus x1. All right. Okay, so if her speed is 60 miles an hour, right? That's her rate, right? So the rate of change is 60 miles an hour. So, oops. So she's gone 60 miles an hour. And now we just need to find out how far. So interstate Michael 240. We need to find out how far she's gone. If she's gone 240, 60 divided by 240, how fast has she gone? So we got to do some division. So let me grab my calculator here. And if my you hear my family in the background, it's bedtime. So they're getting ready for bed. Okay, so let's see. Oh, we got to do this. We got to do this as a function of time because we want to do as a function of time. Okay, so this has to be as a function of time. So mt, right? T minus x of it's x minus x1. So we're going to go t minus t1. So the rate of change is still 60. So our rate of change is 60. So we know that that's going to be our slope. And then actually our initial time, assume t equals 0 at noon. So our initial time is 0. So that's x sub 1. And then y sub 1 is going to be, I believe we got, what are we going to have here? 240. All right. Oops. And why is it 240? Well, it's 240 because at my initial time, I've gone her position is at 240. So if it's noon, at t equals 0 is noon, right? This is where she's at noon. At noon, she's at marker 240. So we're going to start her at 240. So this is the equation we want right here. All right, that's part A. Part B, we want to approximate her position at 2 o'clock. So that's 2 hours after noon. So all we have to do here is we go y equals 60t plus 240. So I just added this over, and then I'm going to plug in 2. All right, so what's that give us? 60 times 2 plus 240, 360. 360 mile marker. So whatever the mile marker is there, that's 360. Okay. Let's see. Infinite Google. Go back. Go back. Okay, so part C. Approximate her position at 10:30 a.m. At 10:30 a.m., geez. So what are we going to do? This is before. This is a case where I guess time is negative. So we got to go negative time here, guys. So 10:30 is going to be roughly about an hour and a half, right? And not roughly, it is. It's an hour and a half before noon. So we're going to go and say for C, t is going to be equal to negative 1.5. So we're going to have y equals 60 times negative 1.5 plus 240. All right, so what does that come out to be? That is 150. What is the domain on which your linear function can be applied? Ooh. Clearly time can be negative if she can have 10:30 a.m., but how far negative can it be? Well, she's traveling 420 miles across the state from north south to north without stopping. So 420 minus 240 is 180. She already traveled 180 miles. Wait, hold on, no. Her position is at so she's already traveled. Sorry, she's already traveled 240. So what does that got to be? We got to backtrack here. We got to backtrack our time. Let's take a look here. -4 hours, it looks like. All right. So we're going to go -4. And then how many hours will it take her to get to 6 to 420? Well, in 2 hours, she's at 360. She travels 60 miles per hour. So that means in 3 hours, she'll be at 420, which is how far she's going. So it's got to be 3 hours. So the domain is -4 to 3. Now, this is kind of weird, right? It's like time is negative. What? Well, that's because we're using t = 0 at noon. So that's kind of a tricky problem here. I think the calculus comes in, guys, where 60 miles per hour, you just got to know that that's the rate. All right, so that's kind of a tricky-ish problem, but it's a problem using local linearization, and local linearization is using a equation of a tangent line to find the to approximate things. I'm not exactly sure if this is a type of a problem that's on there. I think the ones that are on the test are a little bit easier to deal with in terms of the local linearization. All right, let's see what else we're going with. Number 6 was the first one. Looks like number 9. Oh, a lot of people had trouble with number 6 here. 3 and 4 were a couple that someone had some trouble with. Let's go back to 3 and 4. I think those are pretty quick. Yes, this is sketching the graph of f double prime and f using f prime. So I did go over this one in particular with the entire class both of the times. So if I have time, I'll come back to this one because this one only showed up like once in somebody's questions here. So I'll come back to that one if I have time. Sorry, I know you asked the question, but you know I'm only here for a certain amount of time. Got to go bed at some point. So let's look at 20. It looks like 20 was one that a lot of people here had trouble with. So let's take a look at number 20. All right. Oh yeah, this is a good one. Find the dimensions of a rectangle with the maximum area inscribed under the curve y = -x squared plus 12 as shown. So we're looking for maximum area. So don't be fooled that this is some sort of anti-differentiation or some integral problem. This is actually an optimization problem. All right, this is optimization. How do I know it's optimization? Because I'm looking at a rectangle, right? If I was looking at anti-differentiation, I really would be under a curve. I'd be looking at like this entire area, which is not what I'm doing. And plus I'm looking for a maximum area. So here's what you need to do for any optimization problem. The first thing you need to do is figuring out what are you maximizing or minimizing. I am maximizing maximum area. So what I need to do is I need to find a formula for area. Well, what's the formula for area for this rectangle? Well, I'm going to call this y, and I'm going to call this, this little piece right here is x. So this whole piece is 2x, right? So I'm going to call the area the length times the width, right? The base times the height, which in my case is going to be 2x times y, right? This is x. I could call the whole thing x, but it doesn't really make sense in this case because I'm using a function and I only want one side of it. So that's x, that's y. We got 2x times y. That's the area of that rectangle. The area of that rectangle now, we have 2xy. So that's the first thing we need to do is figure out the equation that we want to maximize or minimize. Second, we're going to try to make this into one variable. So we've got 2x and we've got y, but really we only want one variable. But guess what? We know what y equals. Y equals -x squared plus 12. So we're going to go and make a substitution. And we're always going to, for optimization problems, you're always going to find whatever, you're always going to have your whatever you're maximizing and or minimizing. And then you're going to make a substitution using something else to make sure that you have everything in one variable. Okay, one variable only. So the area is equal to 2x times negative x squared plus 12, which we can simplify to negative 2x cubed plus 24x. Now that we have it in one variable and we have it in a bit of a simplified form, we're going to take the derivative, a prime, negative 6x squared plus 24. And then we're going to set that equal to 0 because we're doing a max-min problem, and max-min's, again, finding critical numbers. So we have negative 6x squared equals negative 24. Divide by negative 6. X squared equals, that looks like 4. And we're going to get x equals plus or minus 2. So find the dimensions of a rectangle. We're looking for the dimensions now. Now, I found that x is plus or minus 2. Notice here it could be 2 here or it could be negative 2 here, but basically it's 2 going left and 2 going right. So we don't really need the negative 1. So what's the dimension of the base? The base here is clearly going to be 4. And what's the dimension of y? Well, we can figure that out by plugging 2 into my original function. So I'm going to have y equals negative 2 squared plus 12, which is negative 4 plus 12, which is positive 8. So the dimensions are 8 by 4. All right? So that's how you do a maximum minimum problem. Remember, the key to maximum, if you see something that says find a blah, 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 where so the maximum or minimizing this, first things first, determine what you're trying to find the min or max of. All right? Second, make an get the equation or the formula for whatever you're trying to maximize or minimize. Then look for something else that you can substitute in so you can make it into one variable. Then take a derivative, set equal to 0, solve. All right, max and mins. All right, let's take a look at another one here. That was 20, 21, 26, 30, 31 looks to come up a couple times here. All right, let's look at 31. All right, 31. Evaluate the following. It says evaluate the following without a calculator. That's really 28, 29, and 30. Okay, guys. 31, you need a calculator. How do you know? Actually, yes. How do I know? It's because I have sine of x cubed. Now, in my class, we haven't done anything with sines yet, right? So if it has a trig function, we're likely going to use the calculator for now. Plus, there's some crazy decimals going on. Anytime we're doing crazy decimals, it's with a calculator. So if you guys were stunned by 31 and going, oh, how am I supposed to do this without a calculator? You're not. It should be clear that evaluate the following without a calculator, that really is only for 28 through 30. Okay? So let's talk about how do you do number 31 with a calculator. So 31 is a span problem, or start plus accumulation. How do I know it's start plus accumulation? Because I'm given the derivative, and I'm looking for a value of the function at a certain point. Okay, I'm actually, that's not, it's this one. I'm looking for the value of a function, and I'm given a value of the function. So those are the three things that if you see them in a problem, it should tip you off that this is a start plus accumulation method. Is I'm given the derivative, I'm looking for a value of a function, and I'm given the value of the function, of the original function, not the derivative of the original function. Okay, so start plus accumulation. This is how it works, right? Start plus accumulation. All right, accumulation means integral. So we're looking for f of 3.6. Our start is going to be whatever's given to us, f of 1.2, right? That's what's given. Then we're going to accumulate from 1.2 all the way up to whatever we're looking for, 3.6. And we're going to do that of f prime. So I'm going to put sine of x cubed here, dx. All right, and I'm going to do this in my calculator. So let me see if I can pull up the calculator here to show you what I'm going to do. It'll take a second for it to load up, and plus it's not very big, so I'll do my best to try to so that you guys can see what it is. But for some reason on my Surface Pro here, it doesn't want to show up very well. Watch it, watch. It's going to get really tiny. I'm not sure if you can see that. I got super tiny. All right. Oh, come on. Okay, let me show you my screen here. Ah. Infinite bias. Okay, let's go back here. Here we go. So I've got this now, f of 1.2. So here's what I'm going to do. I'm going to put 6.25. So 6.25, oops, 25 plus, and then right here, integral, right? That's right here. Integral, which is going to be this little guy right there. All right, 1.2 to 3.6. Make sure that you're in, just because I almost didn't remember this, make sure that you are in radian mode. Oh, I am. Okay, good. Good to go. Sine. So in your calculus, sine is right here in trig. Don't type in sine. It's not going to work. Okay, sine of x. And you're going to lose this little caret key. Come on, caret key. There we go. Sine of x cubed. Yes. All right. Should give it to us 6.295. All right, so I'm just going to write that here. 6.295. All right, so that's how you do it. Let me show you that calculator one more time. I'm sorry I can't make it bigger, folks. Again, that's as large as this. The tablet will let me make it. Let's see if I can make this a little bigger here. That's about it. All right. Okay, so that's how you do that in a calculator. Start plus accumulation method. All right, what else we got here? So I did 30, or I just did 31. Let's talk about 30 because I think that's a good one to do also. It's kind of on the test here. So we got a lot of integration problems on the exam. Remember, just a couple things to talk about before you get set up here. Monomial, what do you do with a monomial? Make sure you split it up, right? When you have a parentheses, the parentheses is raised to a power, you need to use reverse chain rule. Reverse chain rule. Okay. If the parentheses is not to a power, then you don't need reverse chain rule. You just distribute. Let's talk about the absolute value. Now, the absolute value is a tricky guy to do without a calculator because you don't have a method for that, right? Like 28, you can do using reverse chain rule. Let's see. Did anybody ask for that? No. It looked like you guys were kind of okay with those. You know, you can use reverse chain rule for 28. You can use looks like this one. You can do x squared minus 5 times x squared minus 5 because you don't have a 2x out here, and you can't do like 1 over 2x. That doesn't work in a reverse chain rule. So in this case, if it's just squared, just FOIL the sucker out, and you can do that. But for an absolute value, you can't really do that. And so what we're going to need to do for an absolute value is we're really going to just need to graph it and then think about what the area under the curve is. So hopefully you have your graphing shoes on when you come to class tomorrow, and you can graph this bad boy. This is just a V that is shifted this way. 1, right? 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 Yes. Right? Yes. Up 1. And we want to go -1, to 5. 1, 2, 3, 4, 5. Okay. Okay. So we want this area plus this area. Okay. So this is, let's see, the best thing to do is plug in -1, and we're going to get -1 is 2. So this is going to be, this is going to end up at 2 here. So that looks like that looks like 2 by 2. So the area of this guy is 1/2 times 2 times 2, which is just 2. All right, so let me use a different color here. So this area is 2. And what's this area? We've got 1, 2, 3, 4. And this is at 5. So let's go and plug that in. We get 5 minus 1, which is 4. So it's going to be up at 4. All right, so this is at 4. All right, so we got 1, 2, 3, 4. So we got 4 units on the bottom, 4 units up here. 4 times 4 times 1/2, because 1/2 base times height is going to be 8. So this is 8. So then 8 plus 2 is 10. So that integral is equal to 10. So with absolute values, you just got to kind of graph it and kind of figure out what's going on with that. That's the best way I can tell you to do that. Let's take a look to make sure that, yeah, look, see, so just graph it. So absolute values, you're just going to have to graph. I mean, there's no way around it. Okay, I got time for a few more here. Infinite minus. What did I not do? Oh, some more people put some stuff. 2021. I did 20 already, didn't I? Yeah. Okay. Let's look at 21. Do a couple of these here. I still have some time. A point moves along the curve y equals x square root cube root of x, so that the y coordinate is increasing at a rate of 2 units per. I'm going to stop here. It's increasing at a rate, increasing at a rate. The y coordinate is increasing at a rate of 2 units per second. That means we're in time here. So if I see the words increasing at a rate of something per second, I have to think, pound your head and go, that's the related rate. That's a related rate. So I'm going to say dy dt is 2 units per second. At what rate, so we're looking for a derivative, is the x coordinate changing? So we're looking for dx dt. We don't know what that is when x is equal to 8. So we're doing a related rate here. We've got y equals x to the 1/3. So now we're going to take the derivative implicitly with respect to time. Dy dt, the derivative of y is dy dt. The derivative of x cubed is 1/3 x to the -2/3 times dx dt. Don't forget your dx dt. We know what dy dt, it was 2. We know x is 8 to the -2/3, and we're looking for dx dt. Let's see. Let's do some quick math here. This is this 3. I'm going to multiply both sides by 3. I'm going to get 6. 8 to the -2/3. Okay, so 8 to the 1/3. 8 to the 1/3 is 2. 2 to the -2 is going to be 1/4. All right, let me just show you what I did here. I did 1 over the cube root of 8 squared, right? That's what that means. And the cube root of 8 is 2. 2 squared is 4. So I got 1/4. So 6 equals 1/4 times dx dt. And then I'm going to multiply 4 to both sides. And I'm going to get dx dt equals 24 units per second. All right. So related rate, guys. There's a lot of stuff on this test. I know. A lot of stuff. But hey, we're preparing for the AP exam, right? We're preparing for the AP exam. Let's look at, let's see, 6, 20, 21. What did I just do? 21? What did I just do? I just did 21. 23, 31. I think I did already 31, didn't I? I don't even remember what I did, guys. I'm flipping out here. Flipping out. 23. Let's just do it. 23. If x equals 3 is a critical number of the function f, all right? So that means that x equals 3, the derivative is 0. Do you all agree with that? I'm sure you do, because it's right. Okay, when we find critical numbers, we take the derivative and set equal to 0. So at x equals 3, the derivative is equal to 0. That's important information to know. And the second derivative is less than 0. So that means it's concave down. Does f have a local maximum or local? Oh, man, guys, this is just a second derivative test. If this is a critical number, and f prime of x equals 0 at x equals 3, and it's going to be concave down, then boom, what is that? That is a local maximum. Local maximum by the second derivative test. You know, I think this is more of a multiple choice question, so you might see that as a multiple choice question on the test. Bam! Well, that one was nice and quick. Let's see what else we got here, guys. I think I got all of these. 25, 28 through 31. Did I just 28 through 30? Oh, I did 30 and 31. I just told you how to do this one, right? 29. And then 28, again, 28 is a reverse chain rule. Let me do a reverse chain rule for y'all. Yes. So 3x plus 4 raised to the 1/4. And we're doing this from -1 to 4 of dx. So for this bad boy, I'm looking at the derivative of the inside, right? The derivative of the inside is going to be 3. So that's my hook. So what do I need? I need the 3 here and the 1/3 here. Now that I have my hook, hook that thing out. And then I'm going to get 1/3, that's from here, times 3x plus 4. And I'm going to add 1 to that. So 5/4 divided by 5/4 plus c, but no, not really, because I have -1 to 4. All right, let's see. 4. That's going to be 4/15. 3x plus 4 to the 5/4. Evaluated from -1 to 4. We're going to plug 4 in first, and we're going to get, oh, look at this, guys, watch. 3 times 4 plus 4 to the 5/4 minus 4/15 times 3 times -1 plus 4 to the 5/4. Now, if this is a free response question and you do this, done. See ya. I plugged my values in. That's a value. If I ask you to simplify, then we got to do some work. All right. So we got to simplify, then we got to do some work. 3 times 4 is 12. 12 plus 4 is 16. 16 to the 5/4 is going to be, let's see, 16 to the 5/4. 16 to the 1/4, I believe, is 2. So 2 to the 5th is 32 times 4/15 minus -3 is 1. Let's just be 1. So 32 times 4 is 128 over 15 minus 4/15 is 124 over 15. I think that's all you can do. What number is this, guys? This is 28. I know this is riveting, isn't it? It's just the most fun you've had on a Sunday night. Ooh, look at that, I got it right. Okay. Feel good when I get calculus right. 19, 18, 9, 11, 25, 28. Let's take a look at some of those here. 25 and 28. I did 28. Look at that. And then again, reverse chain rule, guys. So if you're having a little bit of trouble with reverse chain rule, looks like a couple people are asking about reverse chain. Oh, check this out. I just got to show you something. I'm gonna throw this. Let me see. Hold on. Let me try to mix them here. Okay. Integral of 3x 2x squared plus 1. I know this. Sometimes this pulls some people up. They go, man, I know that the derivative of the inside is 4x. But, dude, I don't know what to do because this is a 3. It's not a 4. I need a 3. What do I do? Well, don't freak out, for one. And don't say, dude, or bruh, what do I do, bruh? This is what you do, okay? This 3, if it's complicating you, just put it outside the integral. Leave yourself a little space there. And then you've got a little room for the 4. So now you put the 4 in there. So we'll put the 4 in there to make our hook. If we put the 4 in there, then we divide by the 4. And now we've got our hook. And all is right in the world. So we've got 3/4 times 2x squared plus 1 to the 4/3 divided by 4/3 plus c. And I do believe that 3/4 divided by 4/3 is going to be 9/16. 2x squared plus 1 to the 4/3 plus c. Okay, there you go. So don't freak out if the number here does not match the number that you need for the hook. Just throw it out of the integral, okay? You could do that. As long as it's multiplied, you can do that. Okay. Somebody asked for use substitution. Let's see. Is there a use substitution problem on here somewhere? Mean value. Did someone ask for mean value theorem? Mean value theorem is easy peasy, guys. Oh, someone did. Easy peasy, mean value theorem. Easy peasy. So what is the mean value theorem? The mean value theorem just says this. F prime is equal to f of b minus f of a over b minus a, which is a rock, right? A rock. So this is just saying take the derivative, set it equal to a rock, solve. That's it, all right? So you have to figure out a rock for one, and then you have to take the derivative and set it equal to that. So the only tricky thing about this guy here is that the derivative is a chain rule, product rule hybrid here. Because you have to take the derivative of the first, which is 1, times the second, plus the first, which is x, times the derivative of the second, which is 1/2 times 2x minus 1, to the negative 1/2, times it to the inside, which is 2. And then now that you have, this kind of cancels out. Now that you have that, you set that equal to whatever you get from a rock. All right. And a rock, remember, you plug in 5, plug in 1, subtract that to get this. So then once you do that, you're going to end up getting the answer there. Let's see, 18. Just show you that here. All right, so here we go. So you get 7/2 here for that. And notice here was the work that I just did. You equal to 7/2. And this is a calculator type problem. So once you set equal to 7/2, use your calculator to find the x-intercepts. That's how I would do it. Whenever I'm solving a problem like this, if you don't have a CAS version, then you're going to take x over square root of 2x minus 1 plus square root of 2x minus 1. And then you can do minus 7/2, graph that, find out where it hits the x-axis. Okay, so anytime you're trying to solve a problem that you're trying to solve for x, put it in the calculator and find where it hits the x-axis. All right? All right, hopefully that helped. Infinite minuses again. Wouldn't that be just great if we had infinite minuses? It would totally solve my workload issue if I had infinite minuses to help me out. 11, 12, and 20. Another 5 minutes here, guys. 11, 12, and 20. Ooh, this is a fun one. Okay, so we've got the graph of velocity function. All right, this is velocity time. Find the object's acceleration at time 5 seconds. Remember that acceleration is the slope of velocity. So at 5 seconds, here's 5 seconds, we just need to find the slope of this line. Okay, down 3 over 1. The slope of this line is -3. So this would be -3, -3 feet per second squared. Find the speed of the object at time 6 seconds. So we're talking speed. So we're actually since we're looking at velocity, remember that speed is the absolute value of velocity. We're looking at 6 seconds. We're going to go down. What is that value? That's -3. So the actual value of the velocity is -3. So the speed is 3 feet per second squared. I'm sorry, per second. Okay? So notice this came from the slope. That's the slope, where this actually came from the actual value right there. On what interval of time is the object moving right? Well, it's going to move right when the velocity is less than, right? Oh, I got my left and my right wrong. When the velocity is greater than 0. So where is the velocity greater than 0? That's where it's above the x-axis. So that's going to be from 0 to, oops, okay, I messed up, guys. This was 5 right here, but it's the same value. Still a slope of -3 all the way down like that. So 0 to 5, everything is above the x-axis. So on what interval time is the object moving right? From 0 to 5. On which interval is the time object velocity, the object's velocity is increasing. So since we're looking for where the velocity is increasing, we're looking at the slope. Remember that the word increasing implies slope. So we're looking for positive slope of the velocity. So that's going to be here and here. So the slope is positive when the time is between 0 and 2 and 6 and 7. Since b prime of t is greater than 0. On which intervals of time is the object's speed increasing? So remember, the speed is increasing. The speed is the absolute value of velocity. Okay, so where is the speed increasing? Now this, remember the absolute value of velocity. So what's the absolute value of velocity look like? Well, this is going to look the same. All right. The absolute value of velocity, that's going to be here. Let me use it. Okay. So this is going to stay the same. This is going to stay the same. This is going to stay the same. It's all positive, but boom, it's going to bounce like this and then like this, right? So this is absolute value of velocity. So where is that increasing? Well, that looks like it's increasing here and here. All right. So where is the interval where the object's speed is increasing? It's going to be 0 to 2 and 5 to 6. All right. So again, the speed is the absolute value of velocity, and since we're looking at velocity, we're going to look at the absolute value function, which is going to bounce anything that's negative here is going to now come up here as positive. At what time is the object furthest to the right? Okay, furthest to the right. So when the velocity is positive, then the object is moving right. Correct? Yes. When it starts to, when the velocity goes negative, now it starts moving back to the left, right? When the velocity is negative, it moves left. All right, so let's think about this. Let's use some purple here. I'm going to be here. All right, and the velocity is positive, so I'm moving to the right. It's still positive, I'm still moving to the right. It's still positive, I'm still moving to the right. Right here, I start to move to the left. because I'm negative, right? Moving left. So when I'm moving right, moving right, moving right. When it gets to 5, I start to move left, so I'm going backwards. So at what time is the object farthest right? At 5 seconds. Because that's, plus if you think about this, that the area under this curve, since we're doing antiderivatives, is greatest. The integral is greatest from 0 to 5. And once we start doing that, we start getting negative area. Let me shrink this down a bit. All right, t equals 5 seconds. Okay, so it's 9 o'clock for me now. I don't want to stay on too much longer. I think I made it through a lot of these. Mysis, you better pray for me tomorrow, please. Math is hard. Yeah, math is hard, and I know that, guys. But if you're obviously you're one of my students. You guys are all doing a very good job, and just know that the struggles that you have now will get better. Like you will get better and better and better as we go along, and then you're gonna find that come March, actually come April, you're gonna know more math than you ever thought you would know. And even now, I was talking to a student, and we were looking at some of the work that the Math 3, accelerated Math 3 students were doing, and we're like, gosh, I can't believe we did that. That's like easy stuff now, because you just imagine like what you've done in the last couple of months. So, and I just have to reiterate, you guys are doing a very good job. So even if it feels like, oh man, I only knew half of this, that's okay. I don't expect you to have, mastered everything. There are a few students that are doing really, really, that are like way at top, but that's not everyone. You need it. If you're at about a 50%, you're doing a really good job right now. You're getting everything that you really need. So I know that sounds weird, like when is 50% passing, but it is for now, because remember that we're building and we're building and we're building and we're building and we're building. So it's always just important that when you take your test, you show me as much as you know, because that's really what the test is, so that I can see what you know. And then it's a good reflection of what you know now. And then remember that as we get closer to the final exam, that not this first semester final, but the last semester final, that's the key, right? What you know at the end game, at the Super Bowl, at the big game, that's what counts. So how you do as we move through this is practice about getting better and better and better. Okay, so the last thing I want to go over is a use substitution problem, because it did come up a couple times, and I did do, hold on one second. Whoa. I did do a velocity time problems. I think I covered everything I need to cover, but I do want to do a use substitution problem. So make sure you know how to do these, guys. Horizontal and vertical tangents. We're still having some people have trouble, taking implicit differentiation. Okay, so make sure you know how to do implicit differentiation. Just going through these real quickly and seeing if I can remember things that were definitely on the problem. Ooh, 32 and 33, those are really important ones. I think somebody had asked for that too. So let me go over this, and then I'll go over a use substitution, and then I will be out of here tonight, because I know that, I don't want to keep my kids up if they're listening to me upstairs. They're going, what is he? What kind of math is he talking about up there? Okay. A velocity of an object is moving given by this velocity function. If the position at time equals 2 is given by x of 2 equals 3, find x of t. Okay, so this is finding x of t. It's not a spam question. It's actually a, so it's not a start plus accumulation because I'm not looking for x of 4. Like if I was looking for x of 4, then I would be start plus accumulation, but I'm actually looking for the function itself. So what I'm going to do is take the antiderivative of b sub t, the antiderivative, okay? Dt. So the antiderivative of 1/4 t cubed minus 2t plus 1 is going to be 1/4 t to the 4th divided by 4 minus 2t squared divided by 2 plus t plus c. Let's see, this is going to be 1/8 t to the 4th minus, these are cancelled out, t squared plus t plus c, and this is x of t. Now, the reason it gives me this first, this stuff here, is so that I can figure out what c is. So I'm going to say x of 2, which is 1/8 2 to the 4th minus 2 squared plus 2 plus c equals 3. And I'm going to figure that out. That's going to be, let's see, 2 to the 4th is 16. 16 divided is 2 minus 4 plus 2. That's going to be 0. So c is 3. So then I'm going to plug it back in here, and I'm going to say x of t equals 1/8 t to the 4th minus t squared plus t plus 3. Okay, so this is part A, part number 32. Number 33, find the total distance traveled by the object on the interval 0 to 4. So total distance traveled. Man, I tell you, so many people have trouble with total distance traveled. Listen, to determine total distance traveled, this is all you have to do. All right? This is what you have to do. Listen. You need to know if the object changes direction in your interval. And the way that you determine that is you set your velocity equal to 0. Okay? So 1/4 t cubed minus 2t plus 1 equals 0. And I feel like that is going to be a calculator problem. Because I don't think we can solve a t cubed without a calculator at this point in our careers, at least in your career. Let's see, 30, 32. Total oh, look at that. They even did a trickier move here. Total distance is 0 to 4. So it would work if we did what I was telling you to do. So let's just continue here. So I would find out where t is equal to 0 for this. And to do that, I would use my calculator. So let's see if I can show this to you. Okay. So I'm going to make a graph. And I'm going to graph 1/4 of x cubed minus 2x plus 1. All right, and I want it between 0 and 4. It looks like there's 2 spots between 0 and 4. This is going to be a struggle, guys, but we got to do it. Analyze graph. 0. All right, what do we got here? 0.517 and 2.534. Okay. And I'm going to look at this graph here. It's above the x-axis, so it's going to go velocity I'm going to stop doing this in a second because the other way is just so much easier. Positive, negative, positive. Okay, so that means it's going to the right, left, right, between 0 and 4. So this is what you're going to do. You're going to do x sub 0. You're going to figure out what that is, which is 3. X of 0.517. X of 2.534. And x of 4. Your very last one. Okay, so you're going to do your endpoints. You've got a change in direction. So you're going to, whatever you get here, you're going to add these two together. And then it looks like it's going to go to the left again. So this one's going to be smaller. So you want to find the distance here. You might need to subtract if it goes negative. And then these two you're going to add together. And then you're going to add all these two together. Okay, so to find total distance, you actually have to split it up and add those together. Now, remember that total distance is, if you're thinking about it in terms of area, remember that the velocity, the antiderivative velocity, is the position, right? And if we're looking at a velocity time graph, the integral from 0 to 4 of the velocity is the signed area. So it's actually going to give you the area of all of these. But we don't want the signed area, we want the absolute value of that. So the absolute value of that is going to be total distance. So guess what? Here's a new, I guess, a new formula that I didn't really talk about. If you want the total distance, you can find that if you're using a calculator from the integral from a to b of the absolute value of the velocity. So the absolute value of velocity taken from a to b will give you the total distance traveled. So if you're using the calculator, this is what you want to do. You want to do a to b of the t cubed. We're going to do that in the calculator. So we're going to go the integral from 0 to 4. Oops. I don't know why I put double zeros. Of 1/4. You can do a t here, by the way. It'll let you do t. T cubed. Stop doing that. I got a double multiplication there too. What's up with that? Minus 2t through t plus 1. Oh, I forgot to absolute value this bad boy. Okay, so hold on. I got to do this. Oh, come on. Absolute value. dt. Enter. 7.129. All right. So in our case, we're going to get 7.129. So you may use this on the exam. Okay. So the total distance traveled is the absolute value of the velocity from A to B. Now, I do want to reiterate that if you use that, you're going to want to use that on the calculator portion because unless you have a linear equation for your velocity, it's going to be too hard to do this on the non-calculator portion, except if you have the graph and the graph is like some sort of linear type thing, like where you can just find the area under the curve. So let's see. So if you had something like this, where is it? Like this, right? Like this, we would be able to find the total area. Sorry, total distance. All right, so if I wanted the total distance, TD, I would go 0 to 7, and I would do the absolute value of v sub t dt. And I could do that because I can find the area here, which is not hard. I just split it up into rectangle triangles, and then find the area here. And remember, the absolute value was up here, so it's positive. So instead of the positive area and negative area, I use the positive area. And I just add them together, and I get the total distance. So that would work, too, if it's on the non-calculator portion. So sorry, hopefully that didn't really confuse you too much. Okay, so it's 9:15. I've spent an hour. I'm going to do one more problem for you guys. It says I got 3 hours, but I'm not going to do 3 hours. I'm going to do a U substitution problem for you to help you out because I know that was a concern as well. So let's take a look to see if I have a U substitution problem here I can do. Those were the last ones. And I don't see a U substitution on here. Oh, I do. Number 26 is a U substitution. So let's do that one. T times 2t plus 1 to the 1/2 power. Okay, so how do I know this is a U substitution? A couple things. I know this is a U substitution because the derivative of the inside, okay, if the inside is, let's see, let's use orange. If the inside is 2t plus 1, the derivative of that, u prime, is just 2, right? I'm going to put dt. It's just 2. And I have a t here. I don't have a 2. I have a t. And the extra t makes things tricky because I can't use just a reverse. I can't just use a reverse chain rule. So if I can't use a reverse chain rule and there's an extra t going on, so if there's an extra variable there outside the parentheses, that's when we know we're going to have to use U substitution. So we're going to go to use U substitution. I already made the U. The U is 2t plus 1. And what I'm going to do is solve for t. So u minus 1 equals 2t. Divide by 2. And I'm going to get u over 2 minus 1/2 equals t. And then now I'm going to do the derivative. And so I'm going to have 1/2 du equals, the derivative of 1/2 is just 0, equals dt. So now I'm going to make my substitution. So t is this, u over 2 minus 1/2. Okay, that's t. And then this whole thing was just u. It always is going to be that, by the way, guys. Whatever's in the parentheses is going to be your u, okay? All right, so now we're going to, the second step to a u substitution is always going to be distribute this bad boy in here, okay? So we're going to have u to the 3/2 over 2 minus 1/2 u to the 1/2 du. Oh, man, I forgot to do that. Ain't got it. So I gotta substitute this guy right here. 1/2 du. Okay, I'm just gonna throw the 1/2 out here. Okay, this right here is gonna go outside. I don't want to have to mess with it. Okay. So I'm gonna have 1/2. Now let's do the antiderivative. U to the 5/2 over 2. This 2 right here comes from this 2 right here. Okay, and then the 5/2 comes from that. Minus 1/2 u to the 3/2 divided by 3/2 plus c. Okay, so got a lot of stuff going on here. Let's 2 cancel with that guy here. This is going to cancel with this guy here. And I'm going to have, I'm going to multiply this 1/2 in here. I'm going to get 1/10, 2 times the 5, u to the 5/2, minus 1/6, 2 times the 3, u to the 3/2, plus c. And then I'm almost done. Last thing I'm going to do is plug in my u back in, which is 2t plus 1. 2t plus 1 to the 5/2 minus 1/6, 2t plus 1 to the 3/2 plus c. Bam. All right, guys. All right, that's it. I've been here for an hour and 5 minutes. Hopefully, you guys got some good stuff out of this. Infinite Max is coming here. Hold on, let me exit my screen share. All right, there we are. I'm back. So hopefully you were able to get, I did a lot of calculus tonight. So it was a big range of stuff, but hopefully it helps. Tomorrow, if you're in my class tomorrow, be ready with some questions. I will take questions for the first 10 minutes of class, I guess, and before we start the test, and then you'll get to start the test. We won't take more than 10 minutes. That way you have plenty of time to start working on the exam. And good luck, get some rest. And I know some of you are like, I'm not going to get rest. I'm just going to keep studying all night. Just keep studying. But, study for a bit and then get some rest. You get to start the test. Ooh, light's going. You get to start the test tomorrow, and then you still get another day to study. You got Monday to study too. You got Tuesday to study. So you got taking the test over 3 days. So you'll have plenty of time to study over the next 3 days. And then, you do your best. Show me what you got. And then you get some questions answered. If you want me to go over some more things, I'll be in my classroom at lunch. All right, guys. Good luck. Mr. Myers is here with you. Remember, if you get stuck, just think to yourself, what would my S's do? Because almost always, that's going to be the right thing. All right. Catch you guys later. Bye.